Hey Fizz kids, it's Mr. C here, and today we're going to talk about the equations of motion. Up until now, we've pretty much talked about motion verbally, graphically, and visually. Well, now we're going to talk about how we can actually talk about motion mathematically and use equations to solve for motion, rather than always looking at a graph or drawing out a picture of the motion itself. So, the first equation that we're going to sort of look at is what happens when we have uniform motion or constant velocity. And if we remember, in order to have constant velocity, that means we have to have zero acceleration. In our motion diagram, that means that the space in between each of our little dots, each of our time periods, is the exact same. And if we were to draw a position versus time graph, we'd have a nice linear line here, where we have one slope and there's equal displacements in the same amount of time. We also happen to know that the slope of this line is equal to our velocity. We can actually write this in a couple different ways. We basically know that our slope, in this case, is equal to our change in x over our change in time, which is really the same as our change in our y-axis over the change in our x-axis. That's all this triangle symbol here means. It's a delta sign. It just means change. We can rewrite this again as our final position minus our initial position, divided by our final time minus our initial time, or a way that's usually a little more handy, because we don't usually deal with final time and initial time, but we usually deal with our change in our position, all divided by our change in time. But this equation isn't always useful in this form. Sometimes we need to know other things. So our first kinematic equation, we actually solve this equation for our final position. And we get the equation of our final position is equal to our initial position plus our velocity times our change in time. And this is actually a special equation. We can see a relationship between this equation. It's going to tell us a lot about the relationship between our velocity and our position. So if we kind of look at our velocity versus time graph, we know that the area under the curve is just going to be equal to whatever our velocity is times our change in time. And we also know that that area under the curve is equal to our change in position during that time period. So what does this kind of tell us? Well, this means that our displacement is directly proportional to our velocity in time. So if you double one of these, if you double our velocity or you double our time, that means our position is also going to double, which is pretty cool if you think about it, and it's kind of interesting. The next thing that we talked about previously are types of motion or constant acceleration. And when acceleration is present basically with constant acceleration, our velocity equation, delta t over delta x, is only going to give us the average velocity, because velocity is always changing whenever we have an acceleration. That's why our position versus time graph changes. What this also means in terms of position is within each time period, instead of traveling the same amount of distance, we're actually traveling a different distance every time. So like early on right here, we only have a very short displacement that we travel, but once we get further up in the same exact time period, we travel a larger distance. Whenever we have constant acceleration, our velocity versus time graph looks like this beautiful linear line, which is pretty cool. We also know that the slope of that graph is equal to our acceleration. And if we kind of rewrite this like we rewrote our slope equation earlier, we know that this is equal to our change in velocity divided by our change in time, our final velocity minus our initial velocity all over our change in time. And if we rearrange this equation, we actually get our second kinematic equation. Our final velocity is equal to our initial velocity plus our acceleration times our change in time. Pretty cool. Similar to velocity and the relationship between velocity, time, and displacement, the relationship between velocity, acceleration, and time is very similar. It's directly proportional. If we double our acceleration or we double our time, we're going to double that final velocity. Our displacement equation, which is what we had before, told us how far it was. When we had constant velocity, it was just sort of this part of the equation. But now whenever we add acceleration into the mix, our displacement equation becomes this guy here. Becomes our final position is equal to our initial position plus our initial velocity times time plus 1/2 our acceleration times time squared. Pretty crazy. The thing about this, though, is that position has a quadratic relationship with time. So that means if we double our time, we're actually going to quadruple our position if we have constant acceleration. So just as kind of a review, these are our 3 constant acceleration equations. So our first one, velocity is steadily changing. We have Vx is equal to our initial velocity plus our acceleration times time. That's if we want to know what our velocity is. We also have another equation. This is our displacement equation that we saw before, which tells us what our position is over a time period. And we learned that our position changes as the square of the time interval. And finally, if we actually match these two together, so if we solve this first equation for time and we plug it into our second equation, we can rearrange it all to find out how our velocity, acceleration, and displacement are all related without using time, which might come in handy. These equations, eventually you will probably come to learn them all by memory. However, you will always be provided with them on your test. I would say the most important equation, though, or the one that is my favorite, is this guy right here. My 1/2 AT squared equation is what I call it. That's probably one of the most important kinematic equations because you can solve almost every kinematics problem using this equation alone if you needed to. Pretty cool. So, how do we solve problems using these equations? Well, there's a few steps. Step 1 is always draw and label a sketch of the problem, especially if there's more than one phase of motion. So this means maybe the first 3 seconds we're speeding up in our car, and then the last 3 seconds we're slowing down or we're traveling at constant velocity. So it's always important to draw a picture. Always draw a picture and label what everything is. And it doesn't have to be a crazy good picture or a complex picture, just a very simple picture. Maybe it's just a dot, and my car is moving this way with some velocity, and it started at x0, and over some period of time, delta t, it ended at whatever my final position is, and I want to know what the, acceleration is or something like that. That's all the picture has to look like. The next thing you need to do is make a list of the 6 possible kinematic variables. We have our initial position, our final position, our initial velocity, our final velocity, our acceleration, and our time. This is going to come in handy because the first thing you're going to do after that is you're going to fill in this list with what you know and what you don't know. Then, based upon what you know and don't know, you're going to pick the correct kinematic equation that contains the variables you have information for and only one unknown value. Rearrange that equation, and then solve for your final answer. Pretty cool, right? We'll do a few practice problems. Okay, so for our first practice problem, a Saturn V rocket is launched straight up with a constant acceleration of 18 meters per second squared. After 150 seconds, how fast is the rocket moving and how far has it traveled? Well, in this case, step 1 is already done for us. They already drew our picture, and it's beautiful. They have our rocket here, show that we start at 0, we're traveling up, we have some sort of acceleration, and they label sort of what our variables are. So now we have to determine, well, what are our variables? Well, we have our initial position, which in this case is 0, because we start at x equal to 0. Our final position, well, we don't know what that is. That's one of the things that we want to solve for. We want to know how far has it traveled. Our initial velocity is 0 meters per second, and we know this because initially we're just standing at rest, right? Our rocket's just sitting on the ground before it gets launched up. Our acceleration is going to be 18 meters per second squared. Our final velocity is also unknown, and our time is going to be equal to 150 seconds. So we have to figure out how fast is the rocket moving and how far did it go. Well, first we want to figure out how fast it's moving. So we want to figure out what our final velocity is. And we kind of look at our equations. The first equation that our final velocity comes up in is our final velocity. It's going to be equal to our acceleration times time plus our initial velocity. And we don't know what our final velocity is, but we know what our acceleration is, we know what our time is, and we know what our initial velocity is. So all we have to do is rearrange this equation for what we want, which in this case, it already is rearranged for that. which is our final velocity. And now we just plug in our numbers. So our final velocity is going to be equal to our acceleration, which is 18 meters per second squared. And our time is 150 seconds. Then we add on our initial velocity, which is 0 meters per second. We solve this equation, and we find out that our final velocity is going to be equal to 2,700 meters per second. Meters per second. And that's going to be in the positive direction, right? Because we're moving up. So that's what our final velocity is. Now we want to know what our final position is. And looking at what we know, we actually see that our second equation, or my favorite equation, is going to be very useful in solving this. So that equation tells us that our final position is equal to our initial position plus our initial velocity times our time plus 1/2 times our acceleration times our time squared. Plugging in, or I guess figuring out what we know. We don't know what our final velocity is. We know what our initial velocity is, our initial position. We know what our initial velocity is. We know what our initial time is. We know what 1/2 is, hopefully. We know what our acceleration is, and we know what our time is. And it's already solved for our final position, which is exactly what we know. That's how far we've traveled. Now all we have to do is plug in what we know. Our final position is going to be equal to our initial position, which is 0, plus our velocity, which is 0, times our time of 150 seconds, plus 1/2 times our acceleration, times our time squared, which gives us a final position of, let me plug it in real quick. It gives us a final position of 202,500 meters. Holy cow, that's pretty crazy. Our second problem. An airplane is flying initially at 120 meters per second, lands on a carrier deck, and stops in a distance of 91 meters. What is the acceleration? Well, once again, we have a beautifully labeled picture. Your picture does not have to be this creative or this detailed. You could just draw dots for your airplane. Now we have to figure out what we know. Well, our initial position is 0, right? Because we're originally starting at 0. Our final position is going to be 91 meters because we travel 91 meters to the right. Our initial velocity is 120 meters per second. Our final velocity in this case is actually going to be 0 meters per second because we come to a full stop. Anytime we come to a stop, our final velocity will be 0 meters per second. We don't know what our acceleration is because that's actually what we're trying to solve for, and we don't know what our time is. Whenever we don't know what our time is, we only have one equation to use if we're not trying to solve for time, and that's going to be that third equation, which is our final velocity squared equal to our initial velocity squared plus 2 times the acceleration times our change in position. Looking at this equation, we know what our final velocity is, we know what the initial velocity is, we know what our final and initial position are, and all we have to do is solve this for time. So rearranging this equation, or not time, acceleration. Rearranging this equation, we know that Vf squared minus our initial velocity squared is going to be equal to 2 times our acceleration times our change in time. Solving for acceleration, we find that that's going to be equal to our final velocity squared minus our initial velocity squared, all divided by 2 times the acceleration times our change in position. Sorry, not times our acceleration, just times our change in position. Plugging in our numbers there, we find that we get 0 squared minus 120 meters per second squared, all divided by 2 times 91 meters minus 0 meters. If we plug this into our handy dandy calculators, or if you really, really, really wanted to, I don't know why you would, you could do this in your head, we get a final acceleration of negative 79.1 meters per second. And all this negative sign tells me is that my acceleration is pointing to the left, which makes sense because we're slowing down. So if our velocity is pointing to the right, our acceleration should be pointing to the other direction. That is the end of my examples. We will work more in class. Go ahead and answer the video check questions now, and I will see you in class.